So you need to draw two situations. One is the initial situation when the mass is up here, the spring is relaxed. The second one is when the mass is at the maximum compression. You take this as initial, this as final, and then put the y-axis so that you can measure potential energy due to gravity, and then put down this equation. Which one of these are zero?
Ki and kf.
Yeah, it starts from rest, ends at rest. So both of these k's are zero. And then what is initial potential energy?
mgh plus x.
Yeah, mgh plus x. G times x plus h, right? What is the final potential energy?
Half kx squared.
1/2 kx squared. So now you know the mass. So 6x plus 0.42, right? Equals to 1/2 k, which is 20x squared. So you have this equation. Now you have to solve it. So put everything on one side. What is x? X is negative b, which is 6, plus minus square root of b squared, 36, minus 4ac, 32.6. Divided by 2a, which is 40. So there's a negative answer and a positive answer, right? Negative
0.059.
0.59 and positive
0.359.
359. All right, there are two answers. Which one would you pick? What this negative means?
It means it's going up.
Yeah, it says from here, you took the downward as x, right? It means x is positive downward. Negative means that this goes up. So that doesn't happen. In fact, it happens if it goes here and then comes back.
Would that happen only if you let go of the,
No,
or you took the box off?
If this comes down here and bounces back and keeps in contact, let's say glues with the top of the spring, it goes back to that point.
I see.
Right? Because that's when conservation of energy is, right? This potential energy of that mass becomes equal to the total energy here and total energy at that other point. So it goes either 35.9 centimeter down or goes 5.9 centimeter up. Why is that? Why there is asymmetry between them? If you put the mass on top of this until it becomes in equilibrium, how far does it compress the spring?
0.359.
No. Try that. Put mg equal to kx. How much do you get?
mg over, k.
You get 15 centimeter. mg equal to kx. What is x in this case? 6 Newton, the mass, the weight, divided by 40 Newton per meter.
Why are you saying kx equals mg again?
If you put the mass on the spring and make it equilibrium, don't move.
I see. Oh, because
That's
it's going to be equal to
equilibrium
each other then. Right.
Yeah, so I want to show you what is the relationship between these two. So 6 over 40, what is that? It's 1.5 divided by what?
0.15.
0.15 meters, right? 15 centimeter. So this, how much is this? 15 centimeter. It's 20.9, right? It's 20.9 lower than the equilibrium that you get from the mass just sitting there. And then if you go 20.9 on the other side, what do you get? You get to this. Right? From 15, go 20.9, you get to this with 21.9. Basically, that's the equilibrium point when the mass is on spring and then oscillates between these two values.
That's cool.
Yeah. Alright, so this is how much the spring will be compressed. The maximum compression of the spring.
I like that trick where you look at it at equilibrium, and then you can definitely tell which one it is.
Yeah. Alright?